Good day to you, students. How are you doing? Welcome to class. Today, we'll be dealing with the description of waves, speed, frequency, and wavelength. So, let's start the class. Describing waves. We are going to be given a definition to waves by dragging the words into the correct boxes. All right, let's start. Physicist makes use of a model to explain the behavior of light, sound, and other phenomena. A wave can be described with the use of a ripple tank in the laboratory. One way of making ripples on the surface of the water in a ripple tank is to have a wooden bar that just touches the surface of the water. The bar vibrates up and down at a steady rate. This sends equally space-based ripples across the surface of the water. A spherical dipper can produce a different pattern of ripples. The dipper just touches the surface of the water as it vibrates up and down, equally spaced circular ripples spread across the surface of the water. So we check. That's all correct. Now, wavelengths and amplitude. We are to give them a description by filling in the missing words. To represent a wave is to use the method of wavy line used in representing sound waves and electromagnetic waves. These wavy lines show the succession of crests and troughs of which the ripples are made. The representation of a wave can be used to define two quantities. In general, the wavelength of a wave is the distance from one crest of the wave to the next. Wavelength is a measure of distance, all right? And its unit is in meters. The amplitude A of a wave is the maximum distance that the surface of the water is displaced from its undisturbed level. That is the height of a crest. Amplitude is also measured in meters. We check. That's correct. Let's move on to the next slide. Frequency and period. We also define frequency and period by dragging the following words into the correct boxes. All right? Frequency is the number of waves sent out each second. Frequency is measured in hertz. 1 hertz is one complete wave or ripple per second. The period which is represented with capital T of a wave, is the time taken for one complete wave to pass a point. The period of wave is measured in seconds. Wave with a short period has a high frequency. Do not forget that. Okay? Wave speed is the rate at which the crest of a wave travels along. Waves can have very different speeds. So we check. That's correct. Now, energy associated with a wave. How do you define the energy associated with a wave? Let's do that by filling in the missing words. In considering waves and energy, the speed of a wave is the speed at which it transfers energy from place to place. The energy from the sun reaches us in form of radiation, that is, light waves and infrared waves. Which travel through the vacuum space and it is absorbed by the earth. For a loudspeaker, it vibrates and causes the air nearby to vibrate. This vibration spread out as sound waves. Energy is transferred from the sound waves to our ears. Energy is also transferred by water waves. So let's check. That is good. So let's deal with the difference between transverse and longitudinal waves through their specific definitions. We are also to drag the words into the correct boxes. A series of compressions travel along a spring. Regions in which the segments of the spring are compressed together. In between the compressions and rarefactions. Regions where the segments of the springs are further apart. This type of wave cannot be demonstrated on a stretched rope. Now, transverse waves are waves in which the particles carrying the wave move from one side to side at right angles to the direction in which the wave is moving. Alright? Longitudinal waves are waves in which the particles carrying the wave move back and forth along the direction in which the wave is moving. Ripples on the surface of water is a transverse wave, while a sound wave is a longitudinal wave. So we confirm and check. That's correct. Now, let's look at this question closely together. that this with wavelength that is associated with a wave. In 10 waves occupy 15 centimeters. What is the wavelength of the wave? Now, the wavelength of the wave or of any wave is represented with what is called lambda, like this. So lambda, which is the wavelength of any wave, is the total length all divided by number of waves. So what is our wavelength now? The number of waves is 10, while the total length is what? 15.0 centimeter. That means this will go and this what? No, this we still have 10. Yes, that means 5 here, correct? 5 here, 2. 3 divided by 2 gives us 1.5 centimeter. So we now have the wavelength of the wave to be 1.5 centimeters. So let's pick it and check. That's confirmed. Let's move on. Speed, frequency, and wavelength. Don't forget that I used lambda to represent wavelength the other time. So for us to define the speed of a wave, it is equivalent to what? The frequency, which is measured in hertz, multiplied by the wavelength. Wavelength is measured in meters or subunit of centimeters and the likes. So V now is equal to F lambda. Where I wrote A, just using that to represent wavelength. But the original representation of wavelength is what? Lambda, and times means what? Multiplication. V is in this case represent the speed of the wave, F denotes frequency, Y A is represent wavelength. Use as a substitute for what? Lambda. 1 hertz is 1 wave per second. That is defining the unit of what? Frequency. Now, let's deal with this question also that talks about the speed of a wave. And frequency module radio station broadcast signals of wavelength 3.0 meters and frequency 100 megahertz. What is the speed? You know that V is equal to what? F lambda. Let's go from the known to the unknown. F now, which is the frequency, is 100 megahertz. And what is mega in physics or standard form? That is 10 raised to the power 6. So you have 100 times 10 raised to the power 6 hertz. And don't forget that 100 in itself is what? 10 raised to the power 2 times 10 raised to the power 6 hertz. And by the way of our indices, that's 10 raised to the power 2 plus 6 hertz. That gives us 10 raised to the power 8 hertz. Now we have our lambda to be what? 3.0 meters. And our velocity is measured in what? Meters per second. Don't forget that frequency on its own is the what? Inverse of what? Period. So with that, we now have 3.0 times 10 raised to the power what? 8 meters per what? Seconds. That means hours can be rated as what? Per what? Per seconds. So with that, we now have our V to be what? 3.0 times 10 raised to the power 8 meter per what? Seconds as our final answer. We have it there. Let's pick it and check. That's correct. Now, this is the breakdown of what I did here. Speed V is equal to frequency F times wavelength lambda. So 10 raised to the power 6 is termed in what? Mega. If it were to be K, capital K, that would be kilo. That would be 10 raised to the power 3. Don't forget those terms. Then lambda is 3.0 meters. You still have our 3.0 times 10 raised to the power 8 meters per second for the what? Velocity. Now, let's look at this question also together. Okay, so a pianist plays the note middle C whose frequency F is equal to 264 Hz. What is the wavelength of the sound waves produced? So speed of sound in air, that's V for sound, velocity of speed or the speed of sound is 330. Don't forget that V is equal to what? F lambda. We have to look for lambda by way of equals to V over what? F. What's our V? 330. Then divided by 264. With that, lambda becomes 1.25 meters. Do we have it as part of the options? Let's pick it and check. So that is correct. Now, this is the breakdown. We have velocity or the speed to be equation 1. Then we can make from equation 1, make our wavelength the subject of the formula. Then we generate the wavelength. And we have 1.25 meters. Now, a woman tunes her radio to a station broadcasting on 200 meters. What does the 200 meters tell her about the radio wave? Now, from what we did just some moments ago, don't forget that V is equal to what? F lambda. V represents the what? Speed. F represents frequency. And lambda represents the what? Wavelength. So if you listen to a radio station, you know it will be at a specific what? Frequency and at a specific speed. But the wavelength now attached is the 200 meters. Not the amplitude, not the frequency, not the speed, but the what? Wavelength. Let's pick it and check. That's correct. Let's move on. Now, looking at this diagram, the diagram shows a wave which labeled distance is the what? Wavelength. Now, for us to be able to complete a cycle that will generate what? A wavelength. So, more or less, it's always looking like this. If you have something of this nature, it's always look like this. Okay? So, you can either choose between here, the starting point 0 here to this point, or you can invariably choose between this point and this what? And this point. So, if you should look at this, you can choose between this point and what? This point. That makes a complete circle. But if you look at this now, between this point and this point makes a what? Complete circle, up and down. This one is up and down. This one is down and up. You can even make a complete circle between what? D and what? This point. But if you look at it, where it is much more complete is on what? Is on this line, C. So our correct answer here now is what? C. Let's pick it and check. That is it. So before we go today, let's check for the correct statements in each of these two measures that we have. Now, from number 1, we have period is the number of waves sent out each second. That is wrong. Period is the reciprocal of what? Frequency. So it can be the number of waves sent out each second. Frequency is the number of waves sent out each second. That is correct. Okay? Waves with short periods have low frequency. That is wrong. When we short periods, we must always have high frequency, because frequency is the inverse of what? Period. Or period is the inverse of what? Frequency. So let's pick the second option and check and confirm. That is it. Now, we also have to choose the correct statement out of these three. Sound wave is a transverse wave. No, transverse wave does not require material medium. Why? Longitudinal waves will always require material medium. And an example of waves that pass through medium is what? Sound waves. For transverse wave, they do not require material medium. That is why they can pass through vacuum or space. Okay? So that statement is false. Longitudinal waves are waves which are perpendicular to the direction of the oscillations of the particles of the medium. That is wrong. Longitudinal waves are always what? Parallel to the direction of oscillations of the medium. Now, transverse waves are waves which are perpendicular to the direction of oscillation of the particles of the medium. That is true. An example we can see is an electromagnetic waves, is an infrared radiation and the like. So we pick it and we also confirm. That's correct. With this, we've come to the end of this session. Do well to join our website www.edubbey.com for more of our interactive notes and classes. Okay? See you and bye for now.